All right. So instead of using a plain text editor, I'm using an HTML editor today to capture the notes, and whatever I write here, as long as I remember to save it at the end of the class, will be on Moodle, just like that. Okay. So if you guys don't have to copy anything that I have typed here, but whatever I just talked about, but I did not type, write down, you might want to kind of jot down some notes. Today's lecture probably will be screen captured. I do not make any guarantees, because if there's any type of equipment malfunction, or I forget to hit the save button or something like that, then the recording obviously will be gone. So you always want to make backup plans. Okay, so we're going back to backups again. So make sure there's always a plan B and a plan C after plan B. Okay, so the first thing I want to talk about is how to do base 2 conversion. Okay. So let's just talk about binary numbers. It is in your book, but I have not assigned that particular reading yet. So we can just go through today's class, and then you guys can go back and read the textbook, that particular chapter and that particular section, and see if you can understand that material a little bit better after today's class. So we'll basically start with binary numbers. And of course, since this is not a plain text editor, I can actually use heading 1 and all the fancy stuff too. Okay, so now that we're talking about binary numbers, the first thing we want to know is what exactly are binary? What is binary? What does the BI stand for? 2. Very good. So a binary number is based on base 2. Okay. How do you call the numbers that we use on a daily basis? The numbers that you have learned since elementary school. Base 10. It's base 10, or otherwise called decimal. Very good. Very good. Deci means 10, so decimal number means base 10. Now, if you know the other words for different numbers, like octa for 8, we actually have octal number, base 8 numbers. We have even base 16 numbers. There's no one single word component to say 16. 16 is made out of 2 words. It's made out of hexa for 6, deci for 10. So hexadecimal number represents base 16 numbers. Okay, base 16 numbers. Think of the multiplication table that you have to memorize. Okay, that's insane. But binary, on the other hand, is easy. Okay, let me just kind of point out a few not so obvious things about binary numbers. Now, we are all used to the base 10 number. How big is the multiplication table of base 10? Okay. In other words, if I have to spell out all the single-digit multiplications, how many are those? Now, including the obvious ones. 0 times 0 is 0. Okay. 1 times 0 is 0. So this is all the trivial case. And then we have 0 times 1 equals 0. 1 times 1 equals 1. 2 times 1 equals 1. Trivial cases too. Oh. I messed up the trivial one. And then we have 0 times 2 equals 0. 1 times 2 equals 2. 2 times 2 equals 4, etc., etc. And the last item of this multiplication table is 9 times 9 equals 81. Okay? I'm pretty sure you do not remember, and I do not remember either, how long it took to memorize the multiplication table. Even though, if you look at it as a matrix, half of it is a duplicate or a mirror image of the other half. So you only have to remember 1/2 of the table. And with the 1/2 that you have to remember, 2 rows are trivial. Anything multiplied to 0 is 0, and anything multiplied to 1 is itself. But even so, there's still a lot of entries to remember. Now, binary numbers, as the name implies, can only have 2 digits. 2 choices for each digit, 0 and 1. Okay, so we represent values only using zeros and ones. Think about multiplication when you only have 0 and 1. How big is the multiplication table for binary numbers? Okay, 4 entries, right? Because we got 0 times 0 equals 0. 0 times 1 equals 0. 1 times 0 equals 0. 1 times 1 equals 1. That's it. Don't you think that we should have learned the multiplication using binary numbers instead of decimal numbers? I don't think I have any problem memorizing that. How about addition? Do you guys still remember back in first grade or kindergarten, you have to learn how to add 5 to 7. It is 13. No, 5 to 7 is 12. Okay, well, arithmetics. Just to check whether you guys are still awake or not. Anyone who's not chuckling is like, paying attention, right? Okay. So anyway, it is 12. But when you have multi-digit addition, it is not, you don't say it's 12, you say it is 2 with a carry of 1 to the next digit, right? And how many combinations do we have, with additions that will bump it over 10 so that you have to do a carry? Quite a few, okay? Not all the combinations are like that, like 2 plus 2 is 4 with no carry. But there are a few additions that has carries. And then you have to remember, how much, what would be the number, and and 1 is a carry, and so on. What about in binary? Oh, it's easy, right? 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is the funny one. 1 plus 1 is 1 with a carry. That's the way I would write it. Or you can call it 1, 1 if you want to. Okay, that's it. Okay, the only time you generate a carry is when you add 1 to 1. In all other cases, there's no carry.
So if you used it without the words, would it be 1 plus 1 equals 1, 1?
Yes. Okay. In base 2. You have to be very clear that we are dealing with base 2, because when someone sees 1, 1, that person will say, oh, it's 11. No, we don't call that 11 in base 2. We call it 1, 1 in base 2. Okay, very good. Are you guys starting to see why we should have learned base 2 instead of base 10? Okay, unfortunately, we have 10 fingers. So it is base 10. Now, base 10 is kind of nasty in many ways because it's not a power of 2. Okay, 10 is not a power of 2, which means base 2 to base 10 conversion and base 10 to base 2 conversion is not going to be trivial. Yes?
I just want to make a comment that kind of thinking like that, it helps out with algebraic language. You think that way, it makes sense. And it's got to be old way of thinking.
Well, it is the old way of thinking, just packaged in a different way. Yep. Shiny package versus the old kind of brown packaging. Yep. All right. Well, but this stuff is kind of difficult already. Okay, doing calculations using binary number is well out of the scope of this class. What we do want to do is to say, if I give you a binary number, do you know what value it is representing? If I give you a base 10 number, can you convert it back to the binary representation? Now, before we move on any further, it is important to distinguish a value versus the value's representation. Okay? A value is I was tempted to say a value is a value, but I have to pick another word for it. A value is a quantity, okay? But it has no intrinsic representation, okay? So if I want to give you an example of, a quantity, okay, I can give you something like this. Let's say the character Z represents an object. So now we have 1, 2, 3, 4. Okay? 4 of something. Okay? The question is, how can we represent the quantity 4? Well, as it turns out, there are many ways to represent the quantity 4. Okay? If you just use the regular way of representing things, let's talk about money. Okay, $4. How can you represent $4? How many ways there are to indicate that you have $4 in your pocket? $4. Okay, I have two $2 bills. I have 4 $1 bills. I have 16 quarters, and so on. Okay, so you can see that with the limited currency representations that we have, there are already multiple ways to represent the same currency amount, which is $4. Are you guys getting the idea? Okay. So that's why the representation is only a way to represent a particular quantity, but most quantities do not have an intrinsic representation. The other thing you can do is to look at measuring units for length, okay? The simplest stuff. Okay, look at length. How long is this pen? Well, we can say it is about 6 inches long. We can say it is how many centimeters long? About 180, okay? We can say this is approximately 180 millimeters long. Or if you want to use, really archaic, measuring units, you can measure it by, the length of your foot. Okay, what is the fraction of the length of your foot makes up this pen, and so on and so forth. Okay, are you guys getting the idea of the representation versus the quantity that you want to represent? So binary numbers, decimal numbers, octal numbers, hexadecimal numbers, they are all about the representation. Okay, so there are many, many different ways to represent exactly the same thing. Base 2 is has one way, base 10 has another way, and so on. Is that okay so far? Okay. All right. So now we have to actually move on and talk about base 2 representation. Okay. Think of a currency system where you have the following bills and coins. Okay, you have $1. Okay, you have 2, 4. You have 8, 16, and so on one side. On the other side, you can also have 1/2. Okay, so I'll just say half of a dollar, quarter of a dollar, an eighth of a dollar, and so on. So instead of our existing currency system, which is actually very inconsistent, okay, we go from 1 penny to 5, 5 pennies to 10, 10 to 25, 25 to 100, which is a dollar. We go from $1 to $2, rare bills, but they do exist. 2 to 5, 5 to 10, 10 to 20, 20 to 50, 50 to 100, 100 to 200. So it is actually fairly irregular as to the multiplier from one bill to the next. But instead of that, let's just say that we have a system where it is completely consistent. On the positive side or on the whole side, we go from 1 to 2, 2 to 4, 4 to 8, 8 to 16. And on the fractional side, we have half, quarter, eighth, 16th, and so on. Yep.
Don't we already have that system sort of already in place with the amount of memory we have on memory cards?
Yes. Yep, exactly. But I do want to just kind of bring this out so that we can do some exercise. Okay. So using this particular system, how do I represent? Let's say $37 and now this part I have to be very careful because some decimal numbers cannot be easily represented using fractions of powers of 2. So I have to be a little bit careful here. How do I represent this amount using the system that I'm talking about? Okay, using the least number of bills and coins. Okay, so you cannot just say, oh, we'll just use a whole bunch of 1/8 coins. No, we want to use the minimum number. Go ahead.
2 16s, a 2, a 1, and an 18.
Well,
or an 8.
Okay, you are correct, but that's because I forgot to mention that you have all powers of 2 to play with.
Okay.
I'm just using this to illustrate the beginning part, but you can go all the way up to, let's say, 10,024, okay, which is a power of 2. So how would you do it? If I ask you to give me the least number of bills and coins to represent $37 and 37.5 cents, okay, using this particular currency system, how